13.8 billion years ago, something impossible happened. Everything that exists, every atom in your body, every star in the sky, every galaxy spanning billions of light years, exploded into being from absolute nothingness. But here's what breaks every rule of logic. We're about to explore what nothing actually was before that moment. Where empty space didn't exist, where time had never ticked, where the word before loses all meaning. Think about true nothingness for a moment. Not darkness, because darkness is something. It's the absence of light in space that still exists. Not emptiness, because even a vacuum contains quantum fields and virtual particles popping in and out of existence. We're talking about absolute nothing. No space to measure, no time to count, no physical laws, no dimensions, no possibility for anything to happen because there's no stage for events to occur. This is the paradox that haunts modern physics. Our most fundamental question, how did the universe begin, immediately crashes into a logical wall. If nothing existed before the Big Bang, how could the Big Bang happen? Events require time, but time didn't exist. Causes require space, but space hadn't formed. The very act of asking what came before assumes time existed to have a before in the first place. Yet quantum mechanics reveals something that sounds like science fiction, but is experimentally verified reality. Nothing is fundamentally unstable. The quantum vacuum, what physicists call the closest thing to true nothingness, refuses to stay empty. Even in perfect emptiness, energy fluctuations occur spontaneously, borrowing existence from the future and paying it back so quickly that the universe's accounting system barely notices. These aren't just theoretical predictions. Scientists measure these quantum fluctuations in laboratories every day. The Casimir effect proves that empty space between two metal plates exerts measurable pressure. Virtual particles leave detectable signatures in particle accelerators. The quantum vacuum buzzes with invisible activity, creating and destroying particle pairs trillions of times per second in every cubic inch of space around you right now. This discovery transforms our question entirely. If nothingness is impossible, if even perfect vacuum seethes with quantum activity, then perhaps the universe never came from nothing at all. Perhaps it came from something far stranger, a state where the concepts of something and nothing break down completely, where quantum uncertainty makes the boundary between existence and non-existence fundamentally blurred. Modern physics suggests three mind-bending possibilities. First, our universe might be one quantum fluctuation among infinite others, a cosmic bubble in an eternal sea of possibility. Second, consciousness itself might play a role in collapsing quantum probabilities into definite realities, making observers fundamental to existence. Third, mathematical structures might be the only thing that truly exists, with our physical universe being one pattern among infinite mathematical possibilities. Each answer leads to deeper mysteries. If quantum fluctuations created our universe, what provided the quantum fields that could fluctuate? If consciousness selects which reality exists, what observed the universe before conscious beings evolved? If mathematics is fundamental, why does this particular mathematical structure exist rather than others? We're about to journey through quantum foam, explore hidden dimensions, examine the holographic nature of reality, and confront the possibility that time itself might be an illusion. We'll investigate whether parallel universes are colliding with ours right now, whether our cosmos cycles through infinite deaths and rebirths, and whether consciousness might be the universe's way of creating itself. The answer to what existed before the Big Bang will challenge everything you think you know about existence. It will blur the line between science and philosophy, between physics and metaphysics, between the observed and the observer. Reality is stranger than we imagined, and the truth about cosmic origins is hiding in plain sight, written in the quantum structure of empty space itself, the quantum vacuum. When you empty a jar completely, is it really empty? Most people would say yes, but physics reveals something that overturns our deepest intuitions about emptiness. What we call empty space is actually buzzing with invisible activity at scales smaller than atoms. Even in the deepest vacuum between galaxies, where you might find only one atom per cubic meter, space itself refuses to be truly nothing. Scientists discovered this when they tried to cool systems down to absolute zero and remove every last bit of energy. They found something impossible. The energy never reaches zero, even at the coldest possible temperature, -460 degrees Fahrenheit. Quantum fields still vibrate with what physicists call zero-point energy. It's like trying to calm a pot of water, but no matter how much heat you remove, microscopic ripples keep forming at the quantum level. These quantum fields fill every cubic inch of space, creating what scientists call the quantum vacuum. Picture an ocean that looks perfectly calm on the surface, but beneath, countless processes occur in patterns too quick and small to see directly. The quantum vacuum works the same way, appearing empty while hosting constant creation and destruction at scales far smaller than atoms. Here's where it gets strange. These quantum fields can borrow energy from the future to create pairs of particles that pop into existence, dance briefly together, then annihilate and disappear. This happens trillions of times per second in every tiny volume of space around you right now. The borrowed energy gets paid back so quickly, in fractions of a second so small they defy imagination, that the universe's accounting system never notices the debt. Scientists prove this isn't just theory through the Casimir effect. When you place two metal plates extremely close together in a vacuum, the quantum fields between them have less room to fluctuate than the fields outside. This creates a tiny but measurable force pushing the plates together. Empty space literally exerts pressure. Experiments confirm this effect with extraordinary precision, measuring forces as delicate as the weight of a few biological cells. But this discovery raises a profound question. If our observable universe came from quantum fluctuations in a vacuum, what was that vacuum sitting in? What provided the quantum fields that could fluctuate in the first place? We're forced to ask whether even deeper layers of reality exist beneath what we call nothing. Some physicists propose that mathematics itself might be the foundation beneath everything. Not numbers written on paper, but pure mathematical relationships that exist independently of physical reality. In this view, our universe isn't made of matter and energy fundamentally, but of mathematical patterns complex enough to experience themselves. The quantum vacuum would be one such pattern, generating our physical reality through its mathematical structure. Others suggest that the concept of beneath or before the quantum vacuum may be meaningless. The vacuum might simply be the ground state of reality, the lowest energy configuration that can exist. Asking what came before, it would be like asking what's colder than absolute zero. The question assumes a direction that doesn't exist, yet quantum mechanics offers another possibility. The uncertainty principle, which states that certain pairs of properties cannot both be known with perfect precision, applies not just to particles, but to fields and even to the fabric of space-time itself. This means that even a hypothetical state of no quantum fields would be subject to uncertainty, causing fields to spontaneously appear. In this view, true nothingness is impossible because the uncertainty principle forbids it. Any state of perfect emptiness would immediately fluctuate into something. The quantum vacuum isn't a stable emptiness that occasionally produces particles. It's an unavoidable consequence of the fundamental laws governing reality. Nothing cannot exist because existence itself is woven into the deepest mathematical structure of nature. This raises a staggering implication. If nothingness is impossible, then something has always existed in some form. The Big Bang wouldn't represent creation from absolute nothing, but rather a phased transition from one type of quantum state to another. What we call the beginning of time might simply be the earliest moment our current physical laws apply, with something stranger and more fundamental existing in the realm beyond. Virtual particles and borrowed existence. Right now, particles are appearing and disappearing inside your body. These aren't science fiction special effects or metaphors. They're virtual particles, and they're fundamental to how reality operates at its deepest level. Every second, quadrillions of these ghostly entities flicker into existence throughout your cells, live for impossibly brief moments, then vanish without a trace. Virtual particles sound like make-believe, but they produce real, measurable effects that shape the world around you. They're responsible for the magnetic properties of electrons, the way light interacts with matter, and even the force that keeps atomic nuclei from flying apart. Without virtual particles, atoms couldn't exist, chemistry would be impossible, and you wouldn't be here to contemplate these mysteries. Think of virtual particles like cosmic credit cards. They borrow energy from the quantum vacuum, spend it briefly on existing, then pay it back by disappearing. The transaction happens so quickly that it doesn't violate conservation of energy. The shorter their lifetime, the more energy they can borrow. Some virtual particles live for only 1/septillionth of a second, but during that incomprehensibly brief moment, they can carry enormous amounts of energy. The quantum vacuum isn't empty space waiting to be filled. It's a seething substrate where ingredients constantly dissolve and reform. Virtual photons carry electromagnetic forces between charged particles. Virtual gluons bind quarks together inside protons and neutrons. Virtual particles of every type pop in and out of existence, creating an invisible foundation beneath visible reality. Here's the mind-bending part. These virtual particles can sometimes become real. When enough energy gets pumped into the quantum vacuum, virtual particle pairs can separate before they annihilate each other, becoming permanent additions to reality. This happens around black holes, where intense gravitational fields provide the energy needed for virtual particles to escape their quantum debt. Stephen Hawking discovered that black holes actually evaporate through this process. Near the event horizon, virtual particle pairs get separated by gravity's extreme pull. One particle falls into the black hole while its partner escapes into space as real radiation. The black hole loses energy in this process, slowly shrinking until it completely disappears in a final burst of light. This Hawking radiation has been confirmed through theoretical calculations and indirect observations. This process reveals something profound about the nature of existence. If virtual particles can become real when given enough energy, and if our entire universe might have started as a quantum fluctuation, then the boundary between real and virtual becomes surprisingly thin. The distinction isn't absolute, but contextual, depending on energy availability and timescales. Some physicists propose that our whole universe might be virtual in a technical sense, borrowing its energy from a deeper level of reality that we haven't discovered yet. In this view, everything we call real, from planets to people to galaxies, exists on borrowed time in a cosmic quantum fluctuation that started 13.8 billion years ago and hasn't yet been called to settle its debt. But this raises an urgent question. If the universe is borrowing energy, when does the bill come due? The answer involves cosmic inflation, the rapid expansion that stretched our universe from subatomic to cosmic size in its first fraction of a second. During inflation, the universe borrowed enormous amounts of energy from the gravitational field itself. As space expanded, gravitational potential energy became matter and radiation, effectively paying back the quantum debt through the expansion process. The mathematics of this energy exchange are elegant. The positive energy in matter and radiation exactly balances the negative energy in the gravitational field. The total energy of the universe may actually be zero, which means the cosmos didn't need to borrow anything from outside itself. It simply redistributed energy that was already present in the quantum vacuum structure. Yet this explanation pushes the mystery deeper. If virtual particles can create our universe, they might be creating others too. The same quantum vacuum that spawns fleeting virtual particles around us might be spawning entire universes in realms we cannot detect. Each universe would begin as a virtual fluctuation, but some, like ours, would inflate rapidly enough to become permanent realities. This possibility leads us toward one of the most revolutionary concepts in modern cosmology, one that dwarfs even our cosmic beginning and suggests we inhabit just one bubble in an infinite cosmic ocean. The multiverse hypothesis. Our universe might be one bubble in an infinite cosmic bath. Right now, as you contemplate these words, countless other versions of reality might exist in parallel dimensions, some nearly identical to ours, differing only in the position of a single electron, others so strange that the laws of physics work completely differently, making our familiar reality seem mundane by comparison. The multiverse theory emerged when physicists realized that quantum fluctuations don't have to stop with creating one universe. If the quantum vacuum could produce our cosmos, it could produce others. The mathematics suggest it must produce others constantly and endlessly, like bubbles forming on the surface of an infinite sea. Each universe would begin with its own Big Bang, expand through its own version of cosmic inflation, and develop its own unique properties. Some might have stronger gravity, making stars burn faster and die younger. Others might have weaker electromagnetic forces, preventing atoms from forming at all. Most would be sterile wastelands where complexity never develops, but a few might harbor forms of life we cannot imagine. Picture an eternal cosmic ocean where every possible wave eventually forms. Our universe is just one wave in this ocean, temporary and unique but not special. The multiverse doesn't care about our existence any more than the ocean cares about individual drops of water. We exist simply because the conditions happen to be right in this particular bubble. Some versions of multiverse theory suggest there are infinite universes, which means every possible variation of reality exists somewhere. There's a universe where dinosaurs never went extinct. There's a universe where gravity repels instead of attracts. There's a universe where the fundamental constants are different enough that stars never form, and another where they're tuned so precisely that life emerges on nearly every planet. These parallel realities aren't science fiction fantasies. They emerge naturally from our best mathematical descriptions of quantum mechanics and cosmic inflation. When you solve the equations that govern the quantum vacuum, infinite universe creation falls out as an inevitable consequence. Physicists didn't add this feature to make their theories interesting. It appeared whether they wanted it or not. The implications are both breathtaking and unsettling. If infinite universes exist, then every possible tragedy and triumph is happening somewhere right now. Every book that could be written already exists in some universe. Every scientific discovery that could be made has already been made in countless parallel realities. The uniqueness we attribute to human achievement dissolves in the face of infinite repetition. Some physicists push this idea even further, suggesting that the multiverse itself might be just one level in an even grander hierarchy. Perhaps there are infinite multiverses, each containing infinite universes stacked in layers of reality that stretch beyond our ability to comprehend. Max Tegmark's mathematical universe hypothesis proposes that every mathematically consistent structure exists as a physical reality somewhere in this hierarchy. But if parallel universes exist, they might not stay parallel forever. Quantum mechanics suggests that universes could collide, merge, or influence each other in ways we're just beginning to understand. The cosmic microwave background radiation that fills our sky might contain subtle signatures of collisions with other universes that happened billions of years ago. Scientists have searched for these collision signatures, circular patterns, or unusual temperature fluctuations in the cosmic microwave background that can't be explained by processes within our universe alone. Some research teams have claimed detections, though the evidence remains controversial and requires extraordinary proof given the extraordinary nature of the claim. This possibility points toward an even more radical idea about what existed before our beginning. What if our Big Bang wasn't the beginning of everything, but just the latest restart in an eternal cycle? What if universes are born, expand, die, and are reborn in an endless cosmic rhythm that has no ultimate beginning or end? The cyclic universe model offers a different answer to our central question, one that suggests "before the Big Bang" isn't a meaningless phrase, but rather refers to a previous iteration of cosmic existence, the cyclic universe. What if our Big Bang wasn't the beginning, but the latest restart in an eternal cycle? Imagine a cosmic phoenix that dies in flames every trillion, years only to be reborn from its own ashes. Some physicists propose that our universe follows this pattern, cycling through endless rounds of expansion, collapse, and rebirth. In this view, the Big Bang wasn't creation from nothing, but transformation from something that came before. The cyclic universe model suggests that our cosmos expands for billions of years, just as we observe today. Eventually, the expansion slows, stops, and reverses. Gravity wins the ultimate battle, pulling every galaxy, every star, every atom back together in a cosmic collapse called the Big Crunch. But here's the twist. Instead of ending in complete destruction, the Big Crunch becomes a Big Bang. The universe bounces back from maximum compression, erupting into a new cycle of expansion. Time doesn't end during this transition. It continues through what physicists call a cosmic bounce. The universe falls toward maximum density, accelerating as it approaches. Then quantum effects provide a repulsive force that launches the universe back into expansion. Think of it like a cosmic trampoline. Our universe falls toward the trampoline surface, accelerating as it approaches maximum density. Then quantum pressure kicks in, launching the universe back up into a new cycle of expansion. Each bounce creates what looks like a big bang from the inside, even though it's really just another oscillation in an eternal rhythm. This model solves several puzzles that plague traditional Big Bang theory. It explains why our universe appears so uniform in temperature and density, without requiring the incredibly rapid inflation that standard models demand. The uniformity would be inherited from the previous cycle, where matter and energy had billions of years to reach equilibrium before the contraction phase began. It also eliminates the uncomfortable question of what caused the Big Bang, because there was no ultimate beginning, just endless cycles. The problem of initial conditions disappears when there are no initial conditions, only a continuous process that has always existed in some form. Recent observations of our universe's accelerating expansion, driven by mysterious dark energy, seem to rule out a future big crunch. The expansion is speeding up, not slowing down, suggesting our universe will expand forever rather than eventually collapse. But cyclic theorists have adapted their models to include dark energy. They propose that dark energy's strength changes over cosmic timescales, eventually reversing from expansion driving to contraction driving. In some versions of cyclic cosmology, each cycle lasts about 1 trillion years. Our current cycle began 13.8 billion years ago, making us relatively young in cosmic terms. We have hundreds of billions of years left before the expansion stops and collapse begins. This gives ample time for stars to form, life to evolve, and civilizations to rise and fall countless times before the cycle resets. Each cycle might not be identical. Small variations could accumulate over cosmic generations, making each universe slightly different from its predecessor. Perhaps the laws of physics themselves evolve slightly with each bounce, or the values of fundamental constants drift over cosmic time. Information might somehow carry over from one cycle to the next, encoded in subtle patterns that survive the bounce. Other cyclic models propose that parallel universes take turns expanding and contracting like cosmic pistons in an infinite engine. While our universe expands, others contract. While others explode into new Big Bangs, we coast through our expansion phase. The multiverse would be a vast machine of interlocking cycles, with energy and information potentially flowing between universes during transition phases. These ideas suggest that the question, what came before the Big Bang, has a simple answer: the previous cycle. But this just pushes the mystery deeper. What started the endless cycling in the first place? Could the cycles ever end? And if information carries over between cycles, does consciousness persist in some form, witnessing the eternal death and rebirth of reality itself? String theory and hidden dimensions. Reality might have 6 invisible dimensions wrapped around every point in space. Right now, as you sit reading this, you're surrounded by dimensions you can't see, touch, or directly experience. According to string theory, these hidden dimensions are curled up so tightly that they exist at every location, in our familiar 3-dimensional world, but at scales far smaller than even our most powerful microscopes can detect. Think of a garden hose seen from far away. It looks one-dimensional, like a line. But zoom in close, and you discover it has a hidden circular dimension wrapped around its length. String theory suggests our universe works the same way. What we experience as 3 dimensions of space plus 1 of time might actually be 4 dimensions unfolded from a reality that contains 10 or 11 total dimensions. These extra dimensions aren't empty space. They're dynamic arenas where the fundamental forces of nature play out. The strength of gravity, electromagnetism, and nuclear forces in our familiar dimensions depends on how the hidden dimensions are curved and twisted. Change their shape and you change the laws of physics themselves. In string theory, the smallest building blocks of reality aren't particles but tiny, vibrating loops of energy called strings. These strings are unimaginably small, about 10 to the negative 35th meters long. That's so tiny that if you scaled an atom up to the size of our solar system, a string would still be smaller than a tree. Each different vibration pattern of these strings creates what we perceive as different particles. An electron is a string vibrating one way. A photon is the same string vibrating differently. A quark is another vibration pattern. It's like a cosmic symphony, where every note is a different fundamental particle, and the laws of physics are the rules governing which harmonies are allowed. But here's where it connects to our cosmic origins. String theory suggests that the Big Bang might have been triggered by collisions between higher dimensional objects called branes. Our entire universe could be a three-dimensional membrane floating in higher dimensional space, like a soap film on the surface of a multi-dimensional bubble. When two branes collide in this higher dimensional realm, the impact releases enormous amounts of energy into each brain. From our perspective inside one of these branes, this energy release looks like a Big Bang. Time and space as we know them begin at the moment of collision, but the branes themselves existed before the crash. This brane collision model explains several mysteries about our universe's beginning. It accounts for the incredible uniformity of the cosmic microwave background radiation without requiring faster-than-light inflation. It also suggests that what we call the Big Bang was actually a transition from one state of the brane to another, not creation from eins der absolute nothingness. The hidden dimensions might even contain parallel branes hosting other universes. These parallel realities could be as close as a millimeter away from us in higher dimensional space, but completely unreachable because we're trapped on our three-dimensional brane. Gravity might be the only force that can leak between branes, which could explain why gravity appears so much weaker than the other fundamental forces. Some versions of string theory propose that brane collisions happen periodically, creating an endless series of Big Bangs in our universe's history. Each collision reheats the universe, potentially erasing most information from previous eras. We might be living after countless previous Big Bangs, with only the most recent one accessible to our observations. The mathematics of string theory are elegant but notoriously difficult to test experimentally. The energy scales where string effects become important are far beyond what our particle accelerators can reach. Critics argue this makes string theory more philosophy than physics, a beautiful mathematical structure without experimental verification. Yet string theory offers something profound, a framework where quantum mechanics and gravity finally work together without producing nonsensical infinities. This suggests we're on the right track, even if we haven't yet found ways to test the theory's specific predictions about hidden dimensions and cosmic origins, eternal inflation, and universe creation. Somewhere in the cosmos, new universes are being born every second. While you've been reading this script, countless Big Bangs have erupted in distant regions of space, each one creating an entire cosmos filled with billions of potential galaxies. This isn't speculation, it's the logical consequence of eternal inflation theory, one of the most successful models in modern cosmology. Traditional inflation theory explains how our universe grew from subatomic to cosmic size in its first fraction of a second. But eternal inflation suggests that this process never actually stops. It just moves from place to place, creating an endless sequence of pocket universes in an ever-expanding multiverse. Picture a pot of boiling water where bubbles constantly form and separate from the surface. Each bubble represents a universe like ours, with its own space, time, and physical laws. The boiling water represents the inflating field that fills the multiverse, forever creating new bubbles of reality. Our observable universe is just the inside of one such bubble. The Big Bang wasn't the beginning of everything, but the moment when our local region of space stopped inflating and began the slower expansion we observe today. Outside our bubble, the cosmic inflation field continues its exponential growth, occasionally spawning new pocket universes when quantum fluctuations cause regions to drop out of the inflating state. This process has no beginning and no end. Even if inflation started at some point in the past, once it begins, it produces infinite future time and infinite space. The multiverse grows so fast that no matter how many pocket universes form, there's always room for infinitely more. For every universe that stops inflating and becomes observable like ours, the inflating regions grow exponentially larger. Each pocket universe could have different physical constants. In some, gravity might be stronger, making stars burn out quickly. In others, the electromagnetic force might be weaker, preventing complex chemistry. Most pocket universes would be sterile, but occasionally one would have the right conditions for complexity and life to emerge. The distances between pocket universes are staggering beyond imagination. They're separated by regions of still inflating space that grow faster than light can cross them. Even if you could travel at light speed forever, you would never reach another pocket universe because the space between you and it expands faster than you can traverse it. We're fundamentally isolated from our neighboring universes by the exponential expansion of the inflating field. But here's the truly mind-bending part. In an eternally inflating multiverse, every possible universe exists somewhere. There's a pocket universe where the laws of physics allow entirely different forms of matter. There's another where time has different properties. There's even one where the constants are tuned so precisely that intelligent life emerges far more readily than in our universe. This infinite proliferation of realities raises profound questions about the nature of existence itself. If every possible universe exists, then possibility and actuality become the same thing. Everything that can happen does happen somewhere in the eternal multiverse. The distinction between real and hypothetical dissolves in the face of infinite actualization. Some physicists worry that eternal inflation makes science impossible by predicting that anything can happen somewhere. If all outcomes occur in some universe, how can we make meaningful predictions? Others embrace it as the most elegant explanation for why our universe seems so finely tuned for complexity and life. We observe friendly conditions not because they're special, but because we couldn't exist to observe unfriendly conditions. But even eternal inflation leaves a deeper mystery unsolved. What is the inflating field made of? Where do the quantum fluctuations that create pocket universes come from? At what point do the laws of physics themselves break down, leaving us unable to probe further into the nature of cosmic origins? The Planck epoch and the breakdown of physics. At the edge of the Big Bang, mathematics itself breaks down. Physicists have traced our universe's history back to within a tiny fraction of a second after the Big Bang began. They can describe the formation of the first atomic nuclei, the birth of the first stars, even the moment when space became transparent to light. But there's one boundary they cannot cross, one moment when all their equations produce nonsense. This boundary is called the Planck epoch, lasting from time 0 to about 10 to the negative 43 seconds after the Big Bang. During this incomprehensibly brief interval, the universe was so hot and dense that quantum effects dominated gravity itself. Space and time became grainy and uncertain, like a photograph enlarged until you can see the individual pixels. At the Planck scale, the smooth fabric of space-time that Einstein described gets shredded into quantum foam. Distances smaller than the Planck length, about 10 to the negative 35 meters, become meaningless. Time intervals shorter than the Planck time, about 10 to the negative 43 seconds, cannot be measured even in principle. The very concepts of distance and duration break down. Think of trying to use a ruler made of atoms to measure something smaller than an atom. The ruler itself becomes the limiting factor. Similarly, when we try to probe the Planck epoch, our concepts of space and time become the limitation. We're attempting to use space-time to understand the origin of space-time itself. This creates what physicists call the singularity problem. Every equation in physics assumes that space and time exist as a background stage where events can unfold. But at the moment of the Big Bang, there was no stage. The stage itself was being created along with the very concepts of moment and creation. Einstein's general relativity, our best theory of gravity and space-time, predicts that all matter was compressed into a mathematical point of infinite density called a singularity. But infinities in physics usually signal that a theory has reached its limits. Reality doesn't actually contain infinities. Our mathematical descriptions just break down when pushed beyond their valid domain. Quantum mechanics suggests that the singularity should be replaced by something else, perhaps a region of maximum possible density where space and time become quantized like energy levels in an atom. But we don't yet have a complete theory of quantum gravity to describe this realm. String theory and loop quantum gravity offer partial answers, but neither has achieved the mathematical completeness or experimental verification needed to claim victory. Some physicists propose that asking what happened before the Planck epoch is like asking what's north of the North Pole. Time itself might have a boundary, a first moment that wasn't preceded by anything. In this view, the Big Bang represents the absolute beginning of temporal existence. and the question, what came before, is grammatically correct but physically meaningless. Others suggest that time might be emergent, arising from more fundamental timeless processes. Just as temperature emerges from the motion of countless atoms, time might emerge from quantum interactions in a deeper reality that doesn't experience duration. Before the Planck epoch, there would be no time, only a timeless quantum state from which temporal reality crystallized. The Planck epoch also represents the moment when the four fundamental forces, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, were unified into a single force. As the universe cooled and expanded, this unified force split into separate forces through a series of phase transitions, like water freezing into ice or steam condensing into liquid. Understanding what happened during the Planck epoch requires solving one of the deepest problems in theoretical physics, unifying quantum mechanics and general relativity into a single coherent framework. Until we achieve this quantum theory of gravity, the first moments of cosmic history remain shrouded in mathematical mystery, accessible only through speculation and incomplete theories. This boundary problem points toward one of the deepest mysteries in all of science, the relationship between information and existence itself, information and the fabric of reality. Before the universe began, where was the information needed to create it? Every particle in your body, every atom in every star, every quantum state in every galaxy contains information. Your DNA carries information about your biological structure. The quantum states of electrons in your brain encode information about your thoughts and memories. The universe is fundamentally made of information, but where did all this information come from originally? Think about a simple hydrogen atom, the most basic element in the cosmos. Even the seemingly simple system contains precise information about the electron's energy level, spin, direction, and orbital characteristics. Multiply this by every atom in every galaxy, and the amount of information in our observable universe becomes astronomical beyond comprehension, roughly 10 to the 90th bits of information. Traditional physics treats information as something that gets encoded into matter and energy that already exist. But quantum mechanics reveals something stranger. Information itself might be more fundamental than the matter and energy that carry it. In quantum systems, the information about a particle's state determines what the particle is, not the other way around. This leads to a paradox that cuts to the heart of cosmic origins. If our universe began from quantum fluctuations in empty space, where did the information content of those fluctuations come from? Empty space shouldn't contain the vast libraries of information needed to specify the properties of billions of galaxies. Some physicists propose that information is conserved like energy, meaning it can never be created or destroyed, only transformed. In this view, the information in our universe must have existed before the Big Bang in some form. But this just pushes the mystery back another level. What stored all that information before space and time existed? The holographic principle offers a mind-bending solution. It suggests that all the information in a three-dimensional region of space can be encoded on the two-dimensional boundary of that region, like a hologram that contains a complete three-dimensional image on a flat surface. Applied to cosmology, this means all the information in our universe might be encoded on its boundary at the cosmic horizon. From this perspective, our three-dimensional reality might be a projection of information stored on a distant two-dimensional surface. We could be living inside a cosmic hologram without knowing it. The depth we perceive, the volume we measure, the solid matter we touch, all of it could be emergent properties of information patterns on a boundary we can never reach. This idea emerged from studying black holes, where physicists discovered that information falling into a black hole gets encoded on its two-dimensional event horizon rather than disappearing into the three-dimensional interior. Stephen Hawking initially thought black holes destroyed information, creating a paradox. But subsequent work by Leonard Susskind and others showed that information is preserved on the horizon, resolving the paradox and revealing something profound about the nature of space itself. If space is holographic, then asking where information came from before the Big Bang becomes equivalent to asking what state the cosmic boundary was in. The boundary might have existed in a dormant configuration, containing the potential for our reality but not yet projecting it. The Big Bang would represent the moment when information processing began, transforming potential into actuality. Some versions of the holographic principle suggest that consciousness itself might be the projection mechanism, transforming boundary information into experienced reality through the act of observation. In this view, conscious beings aren't separate from the holographic projection. They're part of the processing system that creates the projection. This leads to an extraordinary possibility. If reality is holographic, then the apparent separation between different conscious beings might be an illusion. All observers might be different aspects of a single information processing system, experiencing itself from multiple perspectives simultaneously. The boundary between self and universe dissolves in the holographic paradigm, but this still doesn't explain where the boundary information came from originally. If information is truly fundamental, existing independently of space, time, matter, and energy, then asking where it came from might be like asking why mathematics works. The information simply exists as a basic feature of reality, needing no further explanation. The mathematical universe. What if reality is literally made of mathematics? Right now, you might think you're reading words made of matter, sitting in a physical chair, breathing real air. But according to the mathematical universe hypothesis, you're actually experiencing mathematical structures, so complex they become self-aware. You aren't made of atoms and molecules fundamentally. You're made of numbers and equations that have learned to think. This isn't metaphor or analogy. MIT physicist Max Tegmark seriously proposes that mathematical existence and physical existence are identical. Every electron, every photon, every quantum field is actually a mathematical object. The universe doesn't just follow mathematical laws, it is mathematics. Think about what mathematics really represents. When you use equations to describe motion, you're not creating an approximation of reality. You're discovering the actual structure of reality itself. The equations don't describe something else. They are the something else. Physical objects are mathematical objects that have achieved sufficient complexity to interact with themselves. This idea solves a puzzle that has bothered scientists for centuries. Why is mathematics so unreasonably effective at describing the natural world? Eugene Wigner called this the unreasonable effectiveness of mathematics in the natural sciences. The answer becomes simple. Mathematics works perfectly because reality is mathematics. We're not discovering mathematical approximations to physical laws. We're discovering the mathematical structures that constitute existence itself. But here's where it gets truly mind-bending. If our universe is a mathematical structure, then every possible mathematical structure should also exist as a physical universe. There's a universe based on different geometries where space has 4 dimensions instead of 3. There's a universe where different mathematical constants govern physics. Every mathematical theorem, every possible equation, every conceivable logical system corresponds to an actual universe somewhere in the ensemble of all mathematical reality. Our universe happens to be described by the particular mathematics we observe: quantum field theory, general relativity, the standard model of particle physics. But countless other universes are described by different mathematics. Some might be simple, governed by elegant equations. Others might be incomprehensibly complex, following mathematical rules we couldn't grasp even in principle. From this perspective, the Big Bang wasn't the creation of matter and energy from nothing. It was the moment when a particular mathematical structure became complex enough to support observer moments, conscious experiences embedded within the mathematical framework. You're not a biological creature observing a mathematical universe. You're a mathematical pattern that has achieved self-awareness. This explains what existed before the Big Bang. Mathematics itself existed timelessly in all its infinite complexity and possibility. The ensemble of all mathematical structures was complete and eternal, containing every possible universe as a subset. Our Big Bang represents the moment when observers first appeared within one particular mathematical structure. Time itself becomes an illusion in this view. The mathematical structures that constitute reality exist timelessly, like geometric theorems. We experience time because we're embedded within structures that contain temporal sequences. But from outside the structure, all moments exist simultaneously. Past, present, and future are equally real, different locations in a timeless mathematical landscape. The mathematical universe hypothesis suggests that consciousness isn't something separate from mathematics, but rather what complex mathematics feels like from the inside. When mathematical structures become sufficiently intricate and self-referential, they generate subjective experience. The equations don't just describe conscious beings, they are conscious beings. This raises profound questions about the nature of existence. If all mathematical structures exist, then existence becomes a property of logical consistency rather than physical instantiation. A universe doesn't need to be created or brought into being. It simply exists by virtue of being mathematically possible. The question, why does anything exist rather than nothing, dissolves, because mathematical structures exist necessarily by their very nature. Yet this leaves us with perhaps the deepest mystery of all. Why do we find ourselves in this particular mathematical structure rather than another? Why does consciousness arise in universes with these specific laws rather than simpler or more complex alternatives? Fine-tuning and the anthropic principle. The universe seems designed for our existence, and nobody knows why. Right now, you exist because of the most extraordinary cosmic coincidence in all of science. The forces that govern reality are balanced so precisely that changing any one of them by even a tiny fraction would make stars impossible, atoms unstable, or complexity of any kind completely forbidden. Consider gravity, the weakest fundamental force. If gravity were just slightly stronger, about 1 part in 10 to the 40th, stars would burn through their fuel in millions of years instead of billions, never giving life time to evolve. If gravity were slightly weaker by the same margin, stars would never form at all because gas clouds couldn't collapse under their own weight. The electromagnetic force shows the same impossible precision. Make it a little stronger, and electrons would bind so tightly to atomic nuclei that chemistry would be impossible. Make it weaker, and atoms would fall apart, making molecules and complex structures forbidden by physics itself. The strong nuclear force that holds atomic nuclei together is tuned even more precisely. Change it by just 2% in either direction, and you eliminate either carbon or oxygen from the universe. Without both elements, the chemistry of life as we know it becomes impossible. Even simple organic molecules couldn't form. But the most shocking example involves the cosmological constant that drives dark energy. Quantum mechanics predicts this constant should be 10 to the 120th power larger than observed. Yet somehow it's tuned to almost exactly 0, allowing the universe to exist for billions of years instead of expanding so fast that matter can never clump together to form stars and galaxies. The odds of all these constants randomly falling within the narrow ranges that allow complexity are essentially 0. It's like throwing a dart from 1,000,000 miles away and hitting a target the size of a single proton. The probability is so small that it might as well be impossible. This fine-tuning problem forces us to confront uncomfortable questions about the nature of reality. The anthropic principle offers one answer. It starts with a simple observation. We exist, therefore the universe must be compatible with our existence. This sounds trivially obvious, but it leads to profound implications. The weak anthropic principle simply states that we observe a universe compatible with conscious observers because we couldn't observe any other type. In universes where stars can't form or chemistry doesn't work, there would be no conscious beings to notice the inhospitable conditions. We necessarily find ourselves in a universe that allows consciousness to emerge. The strong anthropic principle goes further. It suggests that the universe must have properties that make consciousness inevitable, not just possible. In this view, the fundamental constants aren't randomly chosen, but are somehow required to have values that ensure conscious observers will eventually appear. The multiverse offers the most widely accepted resolution to fine-tuning. If infinite universes exist with random physical constants, most are sterile wastelands. But we observe a fine-tuned universe because we couldn't exist in any other type. It's a selection effect. We're sampling from the subset of universes capable of producing observers. Yet some physicists propose that consciousness itself might play a role in selecting the physical constants through quantum measurement effects. If observer moments help collapse quantum possibilities into definite realities, then the act of observation might literally tune the universe to be compatible with observers. This participatory anthropic principle suggests that consciousness and physical reality co-evolve together, each shaping the other. The universe creates observers, but observers also participate in creating the specific universe they inhabit through quantum measurement. Before conscious beings evolved, the universe might have existed in quantum superposition of all possible constant values, with consciousness retroactively selecting the life-compatible branch. This raises a disturbing question. If fine-tuning requires either a multiverse or participatory observers, what does this say about the uniqueness and significance of human existence? Dark energy and cosmic destiny. Dark energy shouldn't exist, but it's tearing our universe apart. In 1998, astronomers made a discovery that shattered everything physicists thought they knew about cosmic destiny. Instead of slowing down due to gravity, the expansion of the universe was speeding up. Something was pushing galaxies apart with ever-increasing force, and nobody had any idea what it was. They called this mysterious force dark energy, and it makes up about 68% of everything that exists. Dark energy is invisible, undetectable except through its effects on cosmic expansion, and it completely defies our understanding of how energy should behave. Normal energy gets diluted as space expands, like perfume spreading through a room. Dark energy gets stronger. The leading explanation involves Einstein's cosmological constant, a number he added to his equations to keep the universe static. He later called it his greatest blunder when observations showed the universe was expanding. But the recent discovery of accelerating expansion suggests Einstein's blunder was actually a profound insight into the nature of reality. The cosmological constant represents the energy density of empty space itself. Even perfect vacuum contains energy, and this vacuum energy creates a repulsive force that pushes space apart. It's as if the universe is filled with an invisible substance that makes space itself want to expand. But here's the problem that keeps physicists awake at night. When you calculate how much vacuum energy empty space should contain using quantum mechanics, you get a number that's 10 to the 120th power larger than what we observe. That's not a small error. It's the worst prediction in the history of science, off by more than 100 orders of magnitude. If quantum mechanics were right about vacuum energy, our universe should be expanding so fast that atoms couldn't form, stars couldn't shine, and galaxies couldn't exist. The fact that we're here to ask these questions means that somehow the universe has tuned its vacuum energy to a value incredibly close to zero, but not exactly zero. This fine-tuning is so precise it seems impossible to have happened by chance. It's like balancing a pencil on its point for billions of years while earthquakes shake the table. Yet somehow the universe has achieved this impossible balance, and we have no idea why. Some physicists propose that what we call dark energy isn't vacuum energy at all, but some other field that mimics the cosmological constant's effects. This hypothetical field, called quintessence, would slowly evolve over cosmic time, potentially explaining why dark energy has the strength it does today. But we have no direct evidence for quintessence, and it raises as many questions as it answers. Dark energy might actually be fossil energy from cosmic inflation, the rapid expansion that stretched our universe from subatomic to cosmic size in its first fraction of a second. During inflation, space expanded faster than light, driven by a quantum field called the inflaton. When inflation finally ended, most of this energy converted into matter and radiation. But what if a tiny remnant of the inflaton field still permeates space, providing the gentle push that's accelerating cosmic expansion today? Think of it like ripples from a stone thrown into a pond. Long after the stone has sunk and the initial splash has subsided, tiny ripples continue spreading outward. Dark energy could be the final ripple from the cosmic inflation that birthed our universe, still echoing through space after nearly 14 billion years. But this explanation suggests dark energy should be slowly decreasing. As the universe expands, eventually it should fade away completely, allowing gravity to slow cosmic expansion once again. Our current phase of acceleration would be temporary, a transitional period between the matter-dominated past and an unknown future. Other theories suggest dark energy might be increasing instead of decreasing. If this is true, cosmic expansion will accelerate faster and faster until it tears apart galaxies, solar systems, atoms, and even space-time itself in an event called the Big Rip, potentially occurring in about 22 billion years when expansion becomes infinite and the fabric of reality gets shredded. colliding universes. Other universes might be crashing into ours right now. While you read these words, our universe could be colliding with parallel realities in slow motion, leaving subtle fingerprints across the cosmic sky. These collisions wouldn't destroy galaxies or planets. They would happen so gently that only the most sensitive instruments could detect their traces. According to eternal inflation theory, our universe is just one bubble in an infinite foam of realities. Most of these bubble universes expand away from each other faster than light, making contact impossible. But occasionally, two bubbles might form close enough together that their boundaries touch before cosmic expansion pulls them apart. When universe boundaries collide, they don't explode like car crashes. Instead, they interact through quantum fields that exist on both sides of the collision zone. These field interactions would release energy that propagates through both universes as gravitational waves and radiation. From inside our universe, such a collision would appear as a circular pattern in the cosmic microwave background radiation, the ancient light that fills the sky from the Big Bang's afterglow. The collision zone would create a subtle, warm, or cool spot in this radiation, like a cosmic bruise marking where another reality touched ours. Several research teams have searched for these signatures. In 2010, a team led by Stephen Feeney analyzed data from the Wilkinson Microwave Anisotropy Probe and claimed to find 4 circular patterns that couldn't be explained by random fluctuations. Other scientists disputed these findings, arguing the patterns could arise from statistical noise or systematic errors in data analysis. The controversy highlights how difficult it is to distinguish genuine collision signatures from coincidental patterns. The cosmic microwave background contains millions of temperature fluctuations, and random chance will occasionally produce circular patterns even without universe collisions. Extraordinary claims require extraordinary evidence, and the evidence remains ambiguous. But if parallel universe collisions are real, they could happen multiple times as our cosmic bubble encounters different neighbors during its expansion. Our sky might contain several collision signatures from different parallel realities, each one marking a brief moment of contact with an alternative cosmos. Future observations with more sensitive instruments might resolve the controversy definitively. Here's the truly mind-bending possibility. If universe collisions can happen, they might also be able to exchange information across the boundary. Quantum fields could carry data from one universe to another during the collision process, creating a form of interdimensional communication. The patterns in the cosmic microwave background might encode messages from parallel universes where physics works differently, or where intelligent life evolved under alien conditions. Some physicists speculate that consciousness itself might be able to tunnel between colliding universes under special circumstances. If awareness is a quantum phenomenon, as some theories suggest, then parallel universe collisions might briefly connect the conscious experiences in different realities. This could potentially explain certain anomalous experiences, feelings of déjà vu, memories that don't match recorded history, or intuitions about events that seem to come from nowhere. Perhaps your consciousness occasionally receives echoes from parallel versions of yourself living in nearby universes that briefly touched our reality. These wouldn't be mystical experiences, but physical phenomena arising from quantum field interactions during universe collisions. The boundary between individual conscious experiences would become blurred during collision events. The implications extend beyond individual experience. Entire civilizations in parallel universes might attempt to send messages across dimensional boundaries during collision events. The cosmic microwave background could contain encoded information from advanced beings trying to communicate across the multiverse. Future technology might allow us to decode these interdimensional messages and send replies of our own. This raises profound questions about the nature of reality and identity. If information and even consciousness can leak between colliding universes, then the boundaries we draw between different realities might be more permeable than we imagine. The holographic universe. Your entire reality might be a projection from a distant boundary. Right now, as you experience this three-dimensional world around you, you might actually be observing a hologram projected from information stored on a two-dimensional surface billions of light years away. This isn't science fiction speculation, it's a serious theory supported by cutting-edge physics and observational evidence. The holographic principle emerged from studies of black holes, where physicists discovered something impossible. When matter falls into a black hole, it seems to disappear from our universe forever. But quantum mechanics says information can never be destroyed, creating a paradox that threatened to break the fundamental laws of physics. The solution came from realizing that information falling into a black hole isn't really destroyed. It's encoded on the black hole's two-dimensional event horizon. From our perspective outside the black hole, the information never quite reaches the horizon. Instead, it spreads out across the surface, creating a complete record of everything that ever fell in. The three-dimensional interior can be fully described by information on the two-dimensional boundary. This discovery led physicists to a startling conclusion. If all the information in a black hole's three-dimensional interior can be encoded on its two-dimensional surface, perhaps all the information in any three-dimensional region can be encoded on its boundary. Applied to cosmology, this means our entire observable universe, with all its galaxies, stars, planets, and life forms, might be information encoded on a distant two-dimensional cosmic horizon. We experience three dimensions because that's how the information is processed and projected, but the fundamental reality exists on a surface we can never reach. Think of watching a movie on a screen. The movie appears three-dimensional and full of complex action, but it's actually information patterns on a flat surface. The holographic principle suggests our universe works the same way, with all of reality's complexity emerging from information patterns on a cosmic boundary. Gerard 't Hooft and Leonard Susskind independently developed this idea in the 1990s, and it has since become a cornerstone of string theory through the ADS-CFT correspondence, a mathematical relationship that proves certain three-dimensional universes are exactly equivalent to theories defined on their two-dimensional boundaries. This isn't just philosophy, it's precise mathematics that physicists use to solve problems in quantum gravity. The holographic principle explains several puzzles about quantum mechanics and gravity. It suggests that what we call space might be emergent, arising from quantum entanglement between different regions of the boundary information. Distance in our three-dimensional world would correspond to the degree of entanglement between boundary regions. Space itself wouldn't be fundamental, but a derived concept arising from information relationships. This offers insights into what existed before the Big Bang. If our universe is a holographic projection, then the Big Bang would represent the moment when information processing began on the cosmic boundary. Before this moment, the boundary would have existed in some dormant state, containing the potential for our reality, but not yet projecting it. Some versions of the holographic principle suggest that consciousness itself might be the projection mechanism transforming boundary information into experienced reality through the act of observation. In this view, conscious beings aren't separate from the holographic projection. They're part of the processing system that creates the projection. This leads to an extraordinary possibility. If reality is holographic, then the apparent separation between different conscious beings might be an illusion. All observers might be different aspects of a single information processing system, experiencing itself from multiple perspectives simultaneously. The boundary between self and universe, between observer and observed, dissolves in the holographic paradigm. Recent research has searched for experimental signatures of the holographic principle. If space is fundamentally two-dimensional with three-dimensional experience being emergent, there might be subtle graininess or noise at very small scales. Experiments using laser interferometers have looked for this holographic noise, but haven't found definitive evidence yet. The search continues with increasingly sensitive instrument, the illusion of time. Time might not exist at the most fundamental level of reality. Right now, you feel time flowing from past to future, carrying you forward through moments that seem to unfold in sequence. But this experience might be a convincing illusion created by the complex arrangement of matter and energy in your brain. At the deepest level of reality, time might not exist at all. Think about a movie recorded on film. The individual frames exist simultaneously on the reel, but when played in sequence, they create the illusion of motion and temporal flow. Similarly, all moments in the history of our universe might exist simultaneously in a timeless realm, with consciousness creating the illusion of temporal flow by experiencing these moments in sequence. This idea emerges from studying the fundamental equations of physics. Einstein's general relativity treats time as just another dimension, no different in principle from the three dimensions of space. The past, present, and future all exist equally in what physicists call the block universe. Your birth, your current moment, and your death exist simultaneously in this four-dimensional space-time block. The flow of time is an artifact of consciousness, not a feature of reality itself. Quantum mechanics suggests something even more radical. At the quantum level, events don't happen in a definite sequence until they're observed. Particles can exist in superpositions of past and future states simultaneously. The quantum universe exists in a timeless realm of pure possibility until consciousness collapses these possibilities into experience sequences. Some physicists propose that time emerges from quantum entanglement between different parts of the universe. As quantum systems become entangled, they create correlations that give rise to the arrow of time. The past is the direction of less entanglement, the future is the direction of more entanglement, and the present is the evolving boundary between them. Without entanglement, there would be no time, only a timeless quantum state. This emergence of time from timelessness might explain what existed before the Big Bang. In a timeless realm, there is no before, because there is no temporal sequence. All possible moments, including those we label as before the Big Bang, exist simultaneously in a timeless ensemble. The Big Bang wouldn't represent the beginning of time, but rather the beginning of temporal experience. It would mark the moment when quantum entanglement became complex enough to create the subjective experience of temporal flow. Before this threshold, reality existed in a timeless quantum superposition of all possibilities. The emergence of time would be a phased transition, like water freezing into ice, where the timeless quantum state crystallized into a temporally ordered universe. Consciousness plays a crucial role in this picture. The experience of time might be how information processing feels from the inside. Your brain creates temporal experience by integrating information from past states and predicting future states. Time isn't something you move through, it's something your consciousness constructs through the act of information integration. This suggests that different types of consciousness might experience time differently. An artificial intelligence with different information processing patterns might experience temporal flow in ways completely alien to human perception. A hypothetical advanced alien civilization might have learned to manipulate their temporal experience, speeding up or slowing down their subjective time flow at will, if time is emergent rather than fundamental. Then the question of what came before the Big Bang becomes meaningless, in a deeper sense than we previously understood. It's not just that time began at the Big Bang, it's that the concept of temporal ordering itself emerged from a more fundamental timeless reality. Asking what happened before is like asking what's north of the North Pole, when the concept of north only makes sense on the spherical surface. The physicist Julian Barber has developed a detailed theory of timeless physics, where the universe is a vast space of possible configurations, and what we experience as time is simply a path through this configuration space. Each moment exists independently, and the flow of time is an illusion created by the way these moments are correlated with each other and with our memories. The observer effect and consciousness. What if the universe needs observers to exist? Quantum mechanics presents us with a puzzle that has haunted physicists for nearly a century. Before measurement, particles exist in multiple states simultaneously, spread out in clouds of possibility. But the moment someone observes them, these possibilities collapse into definite realities. The act of observation literally transforms quantum possibilities into classical certainties. This isn't philosophy, it's experimentally verified science. Electrons can be in multiple places at once until detected. Photons can travel through multiple paths simultaneously until measured. The quantum world remains fundamentally uncertain until something interacts with it in a way that forces a definite outcome. The double-slit experiment demonstrates this perfectly. Fire electrons one at a time through two slits, and they create an interference pattern proving they went through both slits simultaneously. But observe which slit. They pass through, and the interference pattern vanishes. But here's the mind-bending question. If observation creates definite reality from quantum possibility, what observed the universe before conscious beings evolved? How could the universe exist for billions of years before the first minds appeared to collapse its quantum possibilities into definite states? The Copenhagen interpretation, developed by Niels Bohr and Werner Heisenberg, simply accepts that measurement causes collapse without explaining the mechanism. It treats collapse as a fundamental feature of nature, but this leaves uncomfortable questions. What counts as an observation? Does it require consciousness, or will any interaction suffice? A photon detector collapses quantum states, but is the detector itself in superposition until a conscious being reads it? John von Neumann proposed that consciousness is indeed required for collapse, suggesting an infinite regress problem. The detector is in superposition until observed by a scientist, who is in superposition until observed by another scientist, and so on. The only way to stop the regress is to invoke consciousness as something fundamentally different from physical systems, a controversial position that most physicists reject. The many worlds interpretation offers a different answer. It suggests that all possible measurement outcomes actually happen, but in parallel universes that split off from each other during every quantum interaction. From this perspective, consciousness doesn't cause collapse. It just selects which branch of the multiverse it experiences. Every time you make an observation, the universe splits into multiple versions with different copies of you experiencing different outcomes. Yet this raises its own puzzles. How does consciousness choose which branch to follow? Why do we experience one definite outcome instead of the superposition of all possibilities? The many worlds interpretation solves the measurement problem by making reality infinitely complex, but it doesn't explain the subjective experience of singular outcomes. Some physicists propose that consciousness itself might be quantum in nature, with the brain's microtubules or other structures maintaining quantum coherence at body temperature. Roger Penrose and Stuart Hameroff developed the orchestrated objective reduction theory, suggesting that quantum gravity effects in the brain cause wave function collapse, linking consciousness directly to fundamental physics. If consciousness plays a fundamental role in quantum mechanics, this transforms our understanding of cosmic origins. Before conscious beings evolved, the early universe might have remained in quantum superposition, existing as all possible histories simultaneously. The emergence of consciousness would represent a phase transition in the nature of existence itself, from unlimited possibility to actualized experience. This participatory universe idea, championed by physicist John Archibald Wheeler, suggests that observers don't just measure reality, they participate in creating it through observation. The universe might be structured as a self-exciting circuit where quantum processes give rise to consciousness, which in turn actualizes the quantum processes through observation. If this is true, then asking what came before the Big Bang becomes equivalent to asking what existed before observation became possible. The answer might be pure quantum potential, waiting for consciousness to transform possibility into actuality. The ultimate answer. We set out to explore the impossible question: what existed before the Big Bang? Our journey has taken us through quantum foam bubbling with virtual particles, infinite multiverses spawning endless realities, and the mind-bending possibility that consciousness itself might be fundamental to cosmic creation. We've discovered that nothing might be impossible, that time might be an illusion, and that our universe might be a holographic projection of information stored on a distant boundary. The answers we found are stranger than any science fiction, yet they emerge from our most rigorous scientific theories and observations. Quantum mechanics tells us that empty space seethes with energy and virtual particles. Cosmic inflation implies that universes are born constantly in an eternal multiverse. String theory reveals hidden dimensions wrapped around every point in space. The holographic principle shows that reality might be fundamentally two-dimensional, with three-dimensional experience emerging from information processing on a cosmic boundary. But perhaps the most profound discovery is that the question itself might transcend our current frameworks of understanding. Asking what came before the Big Bang might be like asking what's north of the North Pole, a question that dissolves when we understand the true nature of space-time. The Big Bang may not represent creation from nothing, but rather a phased transition from one type of quantum state to another, from timeless possibility to temporal actuality. Yet this doesn't make our exploration worthless. By pushing against the boundaries of the knowable, we've glimpsed the deepest connections between mind and cosmos, between possibility and actuality, between something and nothing. We've seen that consciousness might not be an accidental byproduct of cosmic evolution, but a fundamental participant in creating reality itself through quantum observation. 3 compelling frameworks have emerged from our investigation. The multiverse hypothesis suggests our Big Bang was one bubble among infinite others, each with different physical laws. The cyclic model proposes that universes expand, contract, and rebound in endless cycles, with our Big Bang being the latest bounce. The mathematical universe hypothesis argues that reality itself is made of pure mathematics, with physical existence and mathematical existence being identical. Each framework offers a different answer to what existed before. In the multiverse view, an eternally inflating field existed, continuously spawning new universes. In the cyclic view, a previous universe existed that collapsed and rebounded into ours. In the mathematical view, timeless mathematical structures existed, with our universe being one pattern among infinite possibilities. The fine-tuning of physical constants points toward either a multiverse, where we observe the rare life-compatible universe, or participatory observation, where consciousness retroactively selects the constants through quantum measurement. Dark energy, the mysterious force accelerating cosmic expansion, might be leftover energy from the inflation that created our universe, still echoing through space after nearly 14 billion years. The holographic principle suggests that what we call three-dimensional reality might be information encoded on a distant two-dimensional boundary, with consciousness serving as the projection mechanism. Time itself might be emergent rather than fundamental, arising from quantum entanglement between different parts of the universe. Before the Big Bang, there might have been no time at all, only a timeless quantum state from which temporal experience crystallized. The observer effect in quantum mechanics raises the possibility that consciousness doesn't just measure reality, but actively participates in creating it. Before conscious beings evolved, the universe might have existed in superposition of all possible histories, with observation retroactively determining which history became real. This would make consciousness not separate from the cosmos, but integral to its very existence. As we face an uncertain future, these ideas offer both humility and hope. Humility because they reveal how much we don't know about the nature of existence. Hope because they suggest that consciousness might be far more fundamental and enduring than we imagined. If consciousness plays a role in quantum measurement, then every aware moment might be a creative act that helps determine which reality exists. The ultimate answer to what existed before the Big Bang might only come from future civilizations who survive to probe even deeper into the fabric of reality. Until then, we continue exploring the mystery, knowing that every question we ask and every answer we find participates in the ongoing creation of reality itself. The cosmos began in mystery and continues in wonder. We are not separate from this mystery. We are the universe becoming aware of itself, asking questions about its own origin and destiny. In seeking to understand what came before, we participate in the eternal dance between something and nothing, between possibility and actuality, between the questions that consciousness asks and the reality it helps create.